Good evening. How are we doing? All right. I'll stand a little closer to the microphone. So I've been who's used Cassandra? Has anyone used Cassandra before? All right. So for most of you, you're in the right place. I'm gearing this talk towards newcomers. And I'm also trying to, who's a graduate student? Who's any professors? So I'm also trying to include some material here that will relate what we're working on with Cassandra to potential research topics. So there's an interesting mix of introductory material, and then we'll also get into some cutting-edge database topics. So like I said, I've been working on Cassandra for about 5 years. Cassandra comes out of originally a couple research papers from Google and Amazon about databases called Bigtable in 2006 and Dynamo from Amazon in 2007. So Cassandra inherited from these a log-structured storage engine. We store data in files called SS tables, which stands for sorted string tables. We had dynamic creation of data cells in the data tables. So there's no, initially, this is 2008, there's no fixed schema. We had a compaction strategy that came directly from Google's Bigtable paper. And so compaction in a log-structured storage engine, compaction is where we combine the data files to be able to omit obsolete or deleted data. Because we never overwrite data directly, we create new data files with the new version, so the old version is still present on disk. So the compaction process is what lets us combine those and throw away the old versions. So we had a fairly naive compaction algorithm that we called size-tiered. From the Dynamo implementation, we took the ideas of gossip-based cluster management and failure detection. We also took an idea called hinted handoff, which means that if a node in the cluster is down, we will save the updates that it misses and replay them to it later. And also a process called read repair, which means that we'll also check at read time. When I read a row, I'll compare the versions on the different replicas, and if any of them are out of date, I will repair it with the most recent version at read time. So we have a combination of eager repair as well as lazy repair. And it's configurable which one you want to emphasize. Finally, there's a third type of repair called anti-entropy. And what that is it's basically rsync for databases. So we don't send the entire corpus of data across replicas to compare and see if they are consistent. Instead, we'll compute a hash tree and send that hash tree across the network. So it's very bandwidth efficient. So all of this, if you're curious about getting into more detail, all of this is in fairly readable papers. Again, if you search for a Bigtable paper or Dynamo paper, those are pretty easy to find. So some differences that early versions of Cassandra had from these research papers that it was based on, we had a concept called supercolumns, which was an early attempt at having nestable data structures in Cassandra. We also added indexes early on. So both Bigtable and Dynamo are systems where you can only look up a row by its primary key. And so we added column indexes fairly early on because that's just so useful for building applications. And finally, an important theoretical difference is that Cassandra is an eventually consistent system, but it doesn't use vector clocks. So the Dynamo system used vector clocks for conflict resolution. And what this primarily let them do is, if I have a field, for instance, a user record, where I have an email address and I have a cell phone number, and I have two clients, one of them updates the email address, another updates the cell phone number. So what Dynamo used vector clocks was to let us merge those updates. Even though two people were updating the record simultaneously, it would allow us to say, okay, those updates were actually to different pieces of my record, so I'll be able to merge those and keep both changes and not have to throw either one away. Cassandra solves that problem in a different way, because instead of having a single record, instead of being a key value system where all of those fields in the record are kind of stored together, Cassandra splits it up into each column in the row is stored separately and can be updated separately. So we're able to use a simpler timestamp-based conflict resolution. And I wrote this is for people who are coming from a background of, I've read and understand the Dynamo paper, this is a difficult difference for them to wrap their heads around. So I wrote a blog post about this, and the URL is up here. Our initial API for building applications on top of Cassandra, this is a sample. One of the more commonly called methods from our API called getSlice, where I would give you a row key and then a table, or rather a column family that key belonged to, and Cassandra would go and basically rip out all the data from that row that matches what we have, the slice predicate, the third parameter here. So you can see that this is a bit of a clunky way to deal with a database. It's not user-friendly. It's not like anything anyone's ever used before, and it's tedious building applications with this API. So we've been working on making Cassandra easier to use and more powerful over this past 5 years since we started. Today we have thousands of companies building applications on Cassandra, and I'd like to start by giving you a little bit of an overview of what people use it for by focusing on a handful of examples. The first example is eBay. eBay uses Cassandra in a number of different applications, including its red laser analytics service, but possibly I think that their biggest cluster, the most high volume, high traffic application, is what they call social signals, where on an eBay item page, there's buttons for I like this item, or I want this item, or I own this item, and that data is all tracked in Cassandra. eBay also uses Cassandra for a number of different time series use cases, which is a common reason to use Cassandra. It's a common, it's a good application domain for Cassandra. So when I say time series data, what I mean by that is any data set where chronological order is an important component of the data that I'm tracking. So I have 3 examples here. At the top in the green on the black background, user activity on a website. So whether I'm tracking every click and every request, as in this web server log, you can track raw requests in Cassandra, or you can refine that a little more and track things like, here's the activity of your friends on this website. On the left, we have monitoring data, so monitoring a cluster of servers or power meters in a city, or messages sent in a mobile network. So any of this kind of machine-generated data is also a good fit for Cassandra. And at the bottom, we have financial data, another good example of time series. So we have several examples of companies doing all of these things on top of Cassandra. It's a well-studied and well-solved problem in Cassandra. So eBay gave a list of reasons that they chose Cassandra to build their applications on. One of those is multi-data center support. So deploying a single cluster across multiple data centers and having Cassandra keep the replicas in each data center in sync. Cassandra is probably the best service in the world at doing this. What I've tried to represent on this slide is at the top, I have data centers in the cloud. So running on Amazon EC2 or similar cloud-based services. Google Compute Engine just went generally available yesterday. So a popular choice to be able to expand capacity quickly on demand. At the bottom, I've represented some more traditional data centers where you're managing your machines on premise. So this configuration where I have some data centers managed on premise and some data centers in the cloud, with Cassandra replicating between all of these in a heterogeneous configuration, this is actually a fairly common thing to do. So Cassandra is very flexible in how it allows you to configure this replication and what data you want replicated to each data center. We've also done some work to make this replication reasonably efficient. So in particular, when I'm replicating across the WAN, I don't want, if I have 3 copies in the data center over there, I don't want to send 3 copies of the data over the WAN link. That's expensive. So what I'll do is I will send a single copy to one of the replicas and ask him to forward it to the others in that data center. Another reason that eBay chose Cassandra is its support for distributed counters. So there's the important part about this is the word distributed. So when I say a counter, I'm just talking about incrementing an integer in my database when something happens. So whether perhaps I'm tracking the number of times I've served a given ad to a certain demographic. So I just want to, every time someone views that ad, I'll say increment this by 1. So you maybe think, well, that's an easy that's an easy problem. All you have to do is say update counters set count equals count plus 1. Problem solved. In a traditional database, this is an easy problem because you have a single master that all requests are going through. Since Cassandra is a distributed system, and in particular, in a scenario like this, I may have clients incrementing that counter in each data center. So I can't afford to say, this machine here is the master of the count, and everyone has to go through him, because all the clients in the other data centers will have unacceptable latency crossing that WAN link. So what we do instead, it may be too small to see in the back, but what I've tried to represent here is that each counter will split into multiple partitions, one partition for each replica. And each replica knows the count in each partition, but it's only responsible for managing the count in its own partition. So if you look in the upper left, we have a counter where the state is that the A partition has a count of 3, and the B and C partitions have a count of 0. So the total count, the total count for a counter is the sum of the value in each partition. So the value for this counter is 3. In the upper right, we're processing 2 increments. We have 2 clients that want to increment this count by 2. And one of them is talking to A, the replica A, and another is talking to replica B. So each of those increment their partitions. So A increments its partition to 5, and B increments its partition to 2. So note that B only knows about its own increment as well as the previous state. So B thinks the count is now 5 because it was 3 and then it added 2. And A thinks the count is also 5 because it's 3 and added 2. But down at the bottom, we see the final value after these replicas have been able to talk to each other and asynchronously communicate the updates that they received. And now everyone in the cluster agrees that replica A has a value of 5 and partition B has a value of 2, so that sum of the count is 7. So Cassandra in this way allows you to have eventually consistent distributed counters that let you perform updates with local latency in any data center. Sophia, is there a way I could get a glass of water while I'm talking? That would be great, thank you. Another reason that eBay selected Cassandra is Cassandra's support for Hadoop. Has anyone used Hadoop? A couple more hands, okay. So Hadoop is a complementary technology with Cassandra. They work well together. Hadoop allows you to do batch analysis of big data, whereas Cassandra is about low latency, high volume request processing. So, roughly speaking, it's the same as, you can think of Cassandra as an OLTP database, online transaction processing, and Hadoop as OLAP, online analytics processing. So they work well together. What I've tried to diagram here is that you can configure a Cassandra cluster with workload separation for Hadoop batch processing. So you can have, I've colored the real-time application serving machines in blue, and they will replicate asynchronously with the Hadoop machines in green. And so I can hammer the Hadoop machines with sequential scans and long-running batch jobs, and those won't interfere with serving 100,000 requests per second from the blue machines. So that allows me to do this analysis without having to perform an ETL extract, transform, load into a separate cluster. I can do it within a single cluster and let Cassandra manage the workload separation. The next use case I wanted to talk about is Adobe. So they use Cassandra for a product called Audience Manager, which is a web analytics and content management service in the cloud. So they chose Cassandra for a number of reasons that overlap with the reasons that eBay chose Cassandra, but with some differences. In particular, it was very important to Adobe to get low latency from their database. This is a graph of latency in a production Cassandra cluster, not Adobe's actually. It's from a cluster that wishes to remain anonymous. But you can see that 95% of reads are served in under half a millisecond. So that's a nice consistent result that not only do I have low latency, but it's a consistently low latency. I'll talk about some of the things we do to achieve this later on. Adobe also cited the need to be able to scale incrementally and on demand. So Adobe Audience Manager is a new product, or it was when they introduced it. And so they didn't want to have to, thank you. They didn't want to have to deploy a large cluster ahead of demand. They wanted to be able to scale it and add that capacity as it was needed. So I want to illustrate how Cassandra does this. Here I have a 5-node Cassandra cluster, and each node in the cluster divides up the data that it's responsible for into regions called virtual nodes, or vNodes for short. So I've drawn these with each of these has 100 vNodes, and I'll explain what that has to do with replication later on. But for now, we'll just say that they each have 100 blocks of data, and I add a new node to the cluster. What I'll do is I'll actually select a proportional number of vNodes from each other node in the cluster and have them send those to the new node. So what this does is it means that the new node will have the same amount of data on it as the existing nodes after it's performed this operation, which is called bootstrapping. So we end up with everyone now has about 80 vNodes after this is done. So the impact of adding the new node is spread across all the existing nodes. So you can see how as my cluster size grows, the impact of adding a single new node goes down because I'm pulling less and less vNodes from each existing machine. Adobe also called out Cassandra's support for tunable consistency as a reason why they wanted to use it. I'll come back to this and why this is important for delivering availability and reliability in a distributed system. The last example I'll talk about at a high level is Instagram. So they use Cassandra for logging. That was where they first started out using Cassandra. And then this year, they also migrated their notification service to Cassandra. Again, they also cited scalability as an important reason to use Cassandra, but they also called out some other properties. In particular, Cassandra's design or architecture for writes and updates. So I'm going to go into a brief overview of Cassandra's log-structured storage engine here. In particular, Instagram needed a system where writes are durable. So there's actually a surprising number of databases where if you say insert into this table, and the database says, yes, I'm good, the insert is finished, and if there's a power failure, that insert may or may not actually be there. So Cassandra logs or appends each update, each write to a commit log, similar to what traditional databases do, to give you durability even on a single machine. So in the upper left of this diagram, I have a client that says, I want to update a row with primary key K1, and I have some columns that I need to update in that row. So what we're going to do is we're going to append that to the commit log, which is on the lower left. And then we're also, after we append it to the commit log, we're going to put it into a memory structure called a mem table, it's basically a fancy hash table. So notice that I have a dashed line drawn across the middle of the slide here. So above the line is operations happening in memory. Below the line is operations happening on disk. So as more writes come in, I'll keep appending to the commit log. I'll combine them into the mem table. And eventually, my mem table gets full enough that I need to free up some memory. So what I do is I will flush that data to disk. Now remember at the beginning I said that Cassandra stores data in files called SS tables. So this is where SS tables come from. I've taken that data in the mem table, I've sorted it by primary key, and I've written it out to disk. Sorting it by key allows me to perform efficient compactions later on. I'll be able to merge it with other SS tables without having to read the whole thing into memory. I can do it incrementally. So once I've flushed that to disk, I can now clean up or recycle the commit log segment because I've written it to disk now. It's durable on disk. I don't need to replay it if there's a power loss anymore because I've got the SS table now. So because of this design, you can see that Cassandra's never doing random I/O on writes. We're doing sequential I/O appending to the commit log, and we're also doing sequential I/O writing out or streaming out the SS table all at once. So this gives Cassandra very performant writes compared to B-tree-based storage engines, which is most other databases. Instagram has done careful monitoring of their Cassandra clusters and found that they have 99.9999% uptime of that Cassandra data. So that's a pretty good reliability track record. So if I were to summarize what the reasons that people use Cassandra, massive scalability, high performance, reliability and availability, and also ease of use. We've really been starting to focus on ease of use in 2013. So I'll show you what I mean by that right after I talk about some performance numbers. A group of researchers at the University of Toronto in Canada published a paper at the Very Large Databases Conference in last year comparing Cassandra with other NoSQL databases. They also included MySQL as kind of a known quantity, as a control point. In particular, they studied half a dozen different workloads. I've picked this particular one, which combines reads, writes, and sequential scans. So when I say reads, I mean reads of a single row, writes, and sequential scans of multiple rows. That's the distinction there. So I picked this particular workload to put on the slide because it makes Cassandra look best. But all of them, all of the different workloads share the property that Cassandra is at the top. But in particular, what's interesting about this is that a number of databases, in particular MySQL, did just fine on workloads that were 95% reads. But you can see on this one where I'm mixing in a lot of updates, I'm mixing in a lot of sequential scans, MySQL is hugging the y-axis, the x-axis. It's barely doing any operations per second because of the I/O contention that it generates with its B-tree storage engine. You can see that HBase is slower than Cassandra. It's about 4 times slower than Cassandra, but it's also scaling as I increase the cluster size. HBase also has a log structured storage engine, so it can also cope with the contention here reasonably well. The one drawback of this benchmark is that the most well-known NoSQL database is MongoDB, and they did not include that in their research. So DataStax hired a company called Endpoint to repeat the same benchmark, which was done with an open source tool called Yahoo Cloud Serving Benchmark, and include MongoDB this time. So they repeated the benchmark with Cassandra and HBase and MongoDB. Now you'll note that the graph this time is sloping up and to the right. That's because on this graph, I'm increasing the cluster size by 2 for each data point. On this graph, I'm doubling the cluster size for each data point. So that's why it's shaped exponentially instead of linearly. But we have a reproducible result, which is that HBase is still about 4 times slower than Cassandra. So we felt good that we were getting consistent results across these different benchmarking runs. And then MongoDB is about 18 times slower than Cassandra. There's a couple reasons for this. One is that MongoDB deals poorly with workloads or data sets larger than memory because it uses a memory mapped based storage engine. And so once your data set gets larger than RAM, the performance deteriorates quickly. And I specifically told Endpoint, make sure you use a data set larger than RAM because I wanted to make MongoDB look bad. And it worked. But the other reason is that, again, this is mixing reads and writes. And MongoDB has a fairly coarse-grained update locking. If I'm updating a collection or a database, nobody else can either update or read from that database while the update is going on. So that hurts performance in a workload like this as well. So I said that we've been focusing on making Cassandra easier to use in 2013. So these statements on this slide are valid for both MySQL or other SQL dialects, as well as Cassandra. So we added a query language to Cassandra called CQL, or Cassandra Query Language, that's based on SQL. And so there's a large degree of overlap between the two. I can create table, I can create index, I can select from where. All of these are in common between CQL and SQL. The main difference is that Cassandra does not support joins because we're designing for a distributed cluster. We don't want to have to combine and merge data across different machines because we're not going to be able to push out 100,000 requests per second if we have that kind of overhead. So instead, Cassandra encourages denormalization, and it gives you some tools that are not in SQL to do that. In particular, we let you declare a column to be a map or a set or a list, and that allows a lot of patterns of denormalization to become easier, and I'll give an example in a bit. I'm going to switch gears a little bit to talk about how Cassandra delivers the kind of reliability and availability that Instagram is getting from their Cassandra cluster. These are some other people who have run Cassandra and talked about their experience with that in production. Nathan Milford in the bottom center here works for a company called Outbrain. They lost an entire data center, went offline when Hurricane Sandy hit the east coast of the United States a few months ago. And Cassandra was able to keep working because out of the other data centers, and then heal that offline data center when it got power back. On the small end of the spectrum, Jake Luciani in the lower right notes that Cassandra is able to deal with losing individual disks from a machine, as well as losing machines in a cluster or data centers in a cluster. So Cassandra has been engineered to deal with large-scale or small-scale problems. So how does this work? First, I'm going to talk about how it doesn't work. This is how it doesn't work. So this is the kind of architecture that you often get if you start with a single MySQL server or a Microsoft SQL server, and you need to shard it across multiple machines. So you'll say, for each shard, I'm going to have a master server that I've colored light blue, and that's going to replicate to one or more slaves in dark blue. If the master goes down, I'll fail over to one of the slaves, and that will be the new master. And then I'll need some kind of router to tell clients which shard each row that they're looking for lives on. So there's a couple problems with this design. One is that the router is a single point of failure, so you're going to need to harden that. You're going to need to add some kind of redundant capacity and plan for failover there. But I think more important is what's going on in each of the partitions, in each of the shards. Failover is a dirty word for availability, because even if everything goes perfectly, while during that failover process, I can't accept requests because I don't know who the master is. So there's at minimum there's going to be some period of downtime, even if everything goes well. But if things do not go well, there's a lot of messy corner cases that can go wrong. For instance, suppose my master on the left here, it's still running, but it is unable to talk to the other machines in the cluster. So there's a network problem, for instance. And so the rest of the cluster will say, oh, he's dead. You actually can't tell the difference between a machine who can't talk to you and a machine that's dead. So they're forced to conclude that he's dead. We'll elect a new master. So we fail over to a new master, and then the network starts working again. Now I have two machines that think they're masters. So you might think, well, I'm making this example up. It's a theoretical problem. This is actually a problem that has bitten multiple people running MongoDB because this architecture is actually pretty close to what, it's actually a simplified version of how a MongoDB cluster runs. So a fellow from the Python community gave a talk on his experiences with MongoDB, and he explained how they actually did end up with 2 masters for a single shard, and how all hell broke loose when that happened. So further reading, some links at the bottom here on how that happened, and the fallacy when someone tells you the network is reliable, run away. So what Cassandra does instead is it's designed around each replica being able to route requests to the appropriate machines, and so right away we've eliminated the router single point of failure because any machine in the Cassandra cluster can route requests. And so in this diagram, the client is talking to a Cassandra machine in the upper left that doesn't own the data being updated, but it can send that update to the appropriate machines that actually do own that data. So what we use to decide who actually owns the data is a algorithm called consistent hashing. So what we're going to do is we're going to take the primary key of each row, and we're going to hash it. The details of the hashing algorithm aren't super critical. In the past, we've used MD5, but that's actually kind of heavyweight for what we need because we don't need cryptographic properties. All we care about is that we get a nice, even distribution of hashing outputs. So we actually are totally fine with hash collisions. We don't rely on hash values being unique. So that's totally fine. Murmur is a better choice just because it's faster. So Murmur gives us a 64-bit hash value. And then what we're going to do is we're going to assign each node in the cluster, we're going to assign hash values to those nodes as well. Or rather, we're going to assign 64-bit token values that can be compared to the hash values. So in this case, I've assigned each node a token that gives it 25% of my hash space. And so for each row, I can do a binary search against the tokens assigned to the nodes and say, okay, Jim belongs on node C, Carol on node D, Johnny on node A, and Susie on node C. So this solves one part of the problem, which is how do I pick one replica for a given row? But I have a more general problem. I want to pick n replicas. I want to pick an arbitrary number of replicas. So there's actually different ways that you can configure Cassandra to do this. This is actually this part of hashing the keys to a token is called partitioning, and then this is called the replication strategy of figuring out what additional nodes we should store the data on. Both the partitioner and the replication strategy are pluggable in Cassandra. So the default replication strategy is what we call the simple strategy. And so what we'll do is we'll just say, okay, if the first replica is node D, we'll just walk around the token ring clockwise and say the second replica will be on A, the third replica will be on B. Now in practice, we can actually do better than this if you give Cassandra more information about your cluster. In particular, we know that in real-world data centers, failures are not random. Failures are often they are often correlated to something in the physical world. In particular, the rack, a rack of machines, is a common unit of failure. Because a rack will share a power supply, it will share a router or a switch, it will often share cooling. And so if any of those components fail, then we will often use a whole rack of machines at once. So what Cassandra will do is, if you tell it what rack each of your machines is on, it will assign replicas so that at most one replica is in a given rack. And what that gives you is that if you lose an entire rack at once, then you've only lost one replica of any given row, rather than potentially losing two or even all three replicas if I did it naively, as in this diagram. So I mentioned earlier that the unit of data that Cassandra is responsible for is a virtual node. So this is the same concept as the tokens that I mentioned earlier, but we'll actually assign each node multiple tokens. So and that breaks up the range of data it's responsible for into smaller chunks. The consistent hashing algorithm doesn't change. It just works at a less coarse granularity. So I want to now look a little closer at what happens when a client gives a read request to the Cassandra cluster. The node that handles that request, the node that the client chooses to talk to, is called the coordinator. And as I mentioned earlier, it does not have to be a replica of the data. It doesn't have to be one of the replicas of the row being read. So the coordinator will actually tracks how responsive the other nodes in the cluster are. And so it will route the request to the replica that is responding with the lowest latency, that is responding fastest. And then when it gets the data back from the replica, it will forward it back to the client. So as usual, when everything works, it looks good on paper. What happens when things start to go wrong? If the coordinator knows, if this node fails before the coordinator sends it a request, then the coordinator will recognize that it's failed because of our gossip-based failure detector, and it will route the request to a different replica. So that's actually not an interesting case. The interesting case is the node doesn't fail until after the coordinator has selected it and sent it the request. So in that case, we actually have a bit of a hard problem, because I've selected a replica and it didn't respond to me. So I have a couple options. The bad option is just to say it didn't work, sorry. So that's actually what early versions of Cassandra did. But what we do now is something we call rapid read protection. And what we do is after we send that request to the initial replica, we'll actually check how long it takes for that request to finish. And requests that take longer than average will start to get suspicious. And we'll say, okay, you've taken longer than 99% of successful requests now, so you're probably not going to be successful. Something probably went wrong, whether it's a machine failure, a network failure, maybe the JVM just went into a stop the world garbage collection pause, whatever it was that makes it not respond. I don't care what the reason is, I just care that it's not working. So I'm going to pick the next fastest replica, and I'm going to make a redundant request to that one. And then I'll be able to send that back to the client instead of timing out. So this is the effect that has on a cluster in practice. So as you can see in the graph title, what we did here was after halfway through this load test, we killed one of the machines in the cluster. And it's a 4-node cluster. And so that's important because of something I'll get to. But you'll notice that you can configure how aggressive you want Cassandra to be with rapid read protection, and you can disable it entirely. So the blue line that has the really low dip when I killed the machine, that's what happens when you don't do rapid read protection, and the coordinator just has to report failure back to the client after timing out. You'll notice that each of the other lines here is a different aggressiveness of rapid read protection. The orange line is actually always doing a redundant request. It doesn't wait for it to time out. It's always going to do a redundant request anyway. So there's a couple things that's interesting about that. One is that there's a notable performance impact on always doing that redundant request. So the orange line is about 10% lower than the lines for do it after 99th percentile and 95th percentile, and I think the other one is 10 milliseconds is what we used. Another interesting thing about this is that all of the other lines besides the none, they drop by about 25% briefly when I kill the node before recovering. And the reason for that is that I've killed 25% of my cluster's capacity. So all of those coordinators left alive, have a storm of repeated requests against the other machines remaining in the cluster. So there's a spike in the load being generated because of this rapid read protection, and then that goes back to normal once those requests have been satisfied. Besides being able to deal with catastrophic failure of shooting a node in the head, this also smooths out latency. So very early on, I called out Cassandra's support for delivering consistent low latency as one of the reasons Adobe chose Cassandra. So this has an effect on that. So in the upper left, we have doing no rapid read protection. So if you read down about 5 lines, it says latency 99.9th percentile is 50 milliseconds. 95th percentile is 2 milliseconds. So we're more than an order of magnitude between the 95th and the worst case. And the median, in fact, is 0.8, so sub millisecond. But so there's a big difference between the average and the worst case. If you look at the upper right, we've told Cassandra to do speculative retry after when a request is slower than 90% of other requests, then retry it. And so there we've cut 99.9th percentile to 14 milliseconds. So it's still a lot worse than the best case, but it's 3 times better than it was without doing those redundant requests. So at a price of doing redundant requests 10% of the time, I've improved my worst case latency by a factor of 3. I don't have these in a good order to see this, but look at the bottom, where I have 99th percentile. So the worst case latency for 99th percentile is about 20 milliseconds. So it's lower than doing none at all, but it's actually, what is that, about 30% higher than 90th percentile. So I'm being less aggressive at doing redundant requests, and so my latency in the worst case does tend to be a little worse. So the more redundant requests you do, the better your worst case latency will get, the closer it will get to average. Now there's an important lesson on the next step down. If you look at the 75th percentile, so that's saying now I want to do redundant requests 25% of the time. So we've gone from 1% to 10% to now 25%. And you can see that the worst case latency is actually going back up. It's gone from 14.5 at 90th percentile to 16.8 at 75th. And so what's happening there is I'm actually doing enough redundant requests that it's impacting the throughput of my cluster. I don't have enough spare capacity in the cluster to handle all the extra requests that's being generated. So if you look in the middle on the left now, at always, where I set it to always do a redundant request, now my worst case latency's gone all the way back up to 36 milliseconds. So it's more than doubled from the 90th percentile. So what's happening? So that's an even more extreme example of how doing more requests than my cluster has capacity for is impacting not just the throughput, but also the latency that I can expect. So by default, we set it to 99th percentile, which is a very low impact and gets you a lot of the benefits of dealing with node failure and smoothing out some of the worst requests. It's also reasonable, I think, to drop that down to 90th percentile and do redundant requests 10% of the time. Generally speaking, I wouldn't push it past that because of the impact on throughput that you see with these more aggressive values. So far I've just talked about satisfying requests from a single replica. You can also ask Cassandra to contact multiple replicas and compare the results. The reason is that Cassandra allows you to trade off consistency for availability. So you can ask Cassandra to perform a read or a write and acknowledge that successfully after a single replica, which is what I've been talking about most of the time. After a quorum of replicas, which is a majority of the replicas. Local quorum says a majority of the replicas in my local data center. Local one means any replica in the local data center, and so forth. And the interesting property here is that if I do reads and writes that are both at quorum, then I'm guaranteed that the reader will always see the most recent write. So, and since I only require a majority to achieve that, I also have a degree of protection against failure, which is that I can lose, if I have 3 replicas, I can lose one of those and still make progress. And if I drop all the way down to consistency level of 1, I can lose all but 1 replica and still make progress. I might see stale data temporarily, but that's often better than not being able to see any data at all because too many replicas are dead. That said, so even though if I'm doing quorum reads and writes, I will always see the most recent write when I do a read, there's still a potential for race conditions when I'm doing multi-step operations. For example, suppose I am allowing users to register accounts for my application. So I'll have one user say, my algorithm is going to be check to see if the account already exists. If it doesn't, create it. So in the upper left here, I have one user who starts doing that. So he says, does this user exist? And Cassandra says, no, it doesn't. At the same time, I have another user say, does this user exist? Cassandra says, no, it doesn't. Meanwhile, the first user says, well, since it didn't exist, I'm going to insert a new record. I'm going to create the account. Then the other client also says, well, you told me it didn't exist, so I'm going to also create that account. So what happens then is that the second one will corrupt the first one. It will overwrite it. So we don't want this to happen. We want to be able to give some kind of linearizability to these operations, which is to say, I want to separate these operations so that they happen one at a time. A blunt hammer that you could use to solve this problem is to put a locking service into the application and have it use Redis or Zookeeper or something else as a locking service, and then tell them that you must acquire a lock before attempting to create an account. That solves the problem, but it introduces new problems, which is that what happens if a client acquires a lock and then dies before it releases it? Well, now you have to have some cleaning process go through and break locks that we believe are orphaned, and it gets messy. So what we do in Cassandra, instead of adding locking as a primitive, we added something called lightweight transactions. So the syntax is to add if not exists to an insert, or if column X equals column Y on an update. So in our example of the insert, the first client says, insert this if it doesn't exist. Cassandra replies, yes, I was able to apply this lightweight transaction. When the second client says, insert if not exists, Cassandra will reply, no, I was not able to apply this lightweight transaction, and here is the reason why, and then it gives back the row that does exist. So in the update case, you will say update if column X equals Y, and so if that fails, Cassandra will say applied as false, and here is the value of column X that did not match what you told me to expect. So that lets you do a retry loop if your application logic warrants it with an updated value. In this case, the application logic would be to tell the user, sorry, somebody else has that account. You'll have to pick a different username. So what we do is we use a consensus protocol called Paxos to do this. So this is actually a novel application of Paxos, because usually it's used to create a durable activity log. And what we're using it as kind of a transactional sandbox that then gets committed to normal, eventually consistent storage. the best paper to read about Paxos is called Paxos Made Simple. Most of the other papers add a lot of complexity because they're really trying to build an activity log, which doesn't apply to what Cassandra is doing with it. So Paxos Made Simple is the best summary. What this looks like under the hood is we're actually going to make 4 round trips for each Paxos-enabled lightweight transaction. So of the first phase, the first round trip is the leader, which is the Cassandra request coordinator, sends a prepare message to each of the replicas, and they reply with a promise to not accept transactions from any leader with a lower, what we call a ballot in Paxos terminology. In the Cassandra world, a ballot is a version 4 UUID. So each coordinator can generate ballots independently of the others. The next phase is for the leader to propose a transaction and for the replicas to accept it. Then Cassandra will actually check the lightweight transaction condition. So there's that if condition on each insert or update. So this is where Cassandra checks to see if the condition is actually holds true. If it does, then the leader will send a commit, and then the replicas will acknowledge it. So while this is happening, we store the Paxos state on a per table basis and also on a per partition basis. So you see that the primary key of this Paxos state is the row key, which is to say the primary key of the partition being updated, and the CFID stands for column family ID, which is the internal ID of the table being updated. And so we track a bunch of state about the Paxos algorithm. We track the in-progress ballot, and then we also track the most recent commit. And what that lets us do is if a replica is down and misses a number of Paxos operations, then it may come back up and say, hey, leader, you forgot to apply this transaction that was in progress before I failed. The most recent commit lets us tell that replica, no, I didn't forget about it. I actually applied it, but you were down and didn't know that I applied it. So we can skip retrying that transaction. Because of the overhead of doing these 4 round trips, it's recommended that you don't rely heavily on lightweight transactions in your application, but you only use it when the alternative is race conditions that cause corruption. So a couple links here to application design, using eventual consistency without transactions, and also a blog post on the details of how those work. Another relatively new feature to Cassandra is triggers, where we allow you to create a trigger with basically a jar file, and Cassandra will load that into the process, and you can say create trigger on table name and give it the class name. The trigger class has to implement an interface called iTrigger. And you can see from the row mutation and the byte buffer and the column family classes here that this is a very low-level API. It's hooking directly into Cassandra internals to let you augment that mutation with additional changes, either to the table being updated or possibly other tables. So one of the obstacles to building triggers, this is actually probably a 3 or maybe even 4-year-old feature request, and we shipped it in September of this year. So a very new feature, took us a long time to do, because the thing we were concerned about is if I write trigger code that adds new rows to the mutation being processed, how do I provide guarantees that all of those rows will be applied as a group? I don't want to be in a situation where some of the rows were applied and not others, because then I've kind of violated my contract with the author of the trigger. So what we do is we actually use something called batches. Batches are not transactional. In particular, you can see it's totally valid for me to be able to see some rows from the batch get applied and before others. But I will guarantee that all of them do get applied eventually. Either all of them get applied or none of them get applied. So the way we do that is the coordinator that's processing the trigger, after the trigger has run, I have a batch of mutations that are going to be applied. I will send that entire batch. I will pick a random node in the local data center and ask that node to basically become a backup coordinator. And say, I tell that node, if you don't hear back from me within X number of seconds, assume I have failed and replay the batch. If everything goes well, the coordinator sends out the rows in the batch to the different replicas and then tells the batch log, I didn't need you after all, we're good to go. But if there is a failure, then the batch log will take over. The batch log doesn't know which ones were applied successfully, so it will actually send out each row in the batch again, just to be safe. This is fine because individual updates in Cassandra are idempotent. I can apply them multiple times safely. But any rows that weren't written the first time will now be written by the batch log node. I want to talk about some of the storage engine details now. We've gone to a bunch of trouble to move as much as possible out of the Java heap into native memory. Because the single biggest problem with Java services is dealing with heap fragmentation, which causes stop-the-world garbage collection. So we want to manage as much as possible manually off heap. In particular, we keep a lot of data about SS tables after we write them to disk. We keep a bunch of indexes and metadata about that in memory. So when I get a read request on a replica and I go to look that up in an SS table, there's a number of structures that we consult. The first one is we consult a Bloom filter, which is a probabilistic set of the partitions that exist in this SS table. So the Bloom filter will either say, no, I have no data for that partition in this data file, or I probably have some data. So if the Bloom filter says, no, it doesn't exist, we're done. But if it says probably, then we will go and check the partition key cache. And that will either let us skip to reading that partition, or if it's not in the cache, then we'll have to look that up in our index. So again, there's a dotted line here. Above the line is in memory, below the line is in disk. So if there's no cache hit, we'll go and do a binary search against the partition summary, which will let us get to within 128 records of the index on disk. We'll go read that from the disk. We'll then turn that into a compressed offset. So the partition index contains uncompressed offsets. We'll run that through our translation table to what compressed block that corresponds to, and then we can read that from disk. So in particular, the Bloom filter, the compression offsets, and the partition summary are substantial amounts of memory. And so we've moved those off heap, and we manage those with reference counting so that we can free it when the SS table gets compacted. One other thing I'll note is that compression is actually optional, but it's enabled by default. So if you turn it off, then you can skip that last step, and you can save some memory by not having to store compression offsets. But it's almost always a good idea to leave compression on, because what that does is it makes your page cache more effective. Now you're caching compressed blocks instead of uncompressed blocks. So it's like having twice as much RAM in your server in terms of what you can keep in memory. So some of the stuff we're working on for the next release of Cassandra early next year. One is user-defined types. I mentioned that we allow you to say that a column is a set or a map or a list, but those are not nestable. You can't have a map of maps. So user-defined types allow us to make nestable types. So in this example, I have a users table. The user has an addresses column, which is a map of address structures. And the address structure or type consists of 4 fields, including a set of phone numbers. So we added a little bit of extra syntax to CQL to allow dealing with that. In particular, you'll see at the bottom in the select statement, I say select addresses.city. So I don't need to select everything out of addresses. I can just grab the city field, and that comes back in the result set appropriately. We're also adding collection indexing. So until 2.1, you can't create an index of the contents of a collection column. So in this case, we have a set of tags that I want to index, and that's done for 2.1. That's working. So with these changes, we're blurring the lines a little bit of what Cassandra is. Yes, it's a partitioned row store. You have rows and columns, but columns can be maps as well as primitives. They can be user-created types as well as primitives. You can think of it as a document database like what's the XML? MarkLogic. You can think of it as a document database like MarkLogic or MongoDB, except that it's strongly typed. You can't put arbitrary data into a Cassandra map, but you can put an address into a map, and Cassandra will require you to define that up front. You could also think of Cassandra as an object database. And the truth is it's a little bit of all these things. Cassandra really is a general purpose database that's successful at solving problems in many industries. Another thing we're working on for 2.1 is more efficient repair. What we do now is when I repair replicas, which is to say I want to compare replica A's data with replicas B's data for the same partition ranges. So what I'm going to do is I'm going to build that hash tree of all the data for the range that I'm repairing. And then what I can do is I can just look at the head of that tree, and if the head matches across both replicas, then I know they're consistent. If they don't match, then I can look at the left child and the right child, and so I can drill down and find where the difference is coming from, and then I send just those blocks of data across the wire. So the problem is that when I add more data to Cassandra, I have more SS tables, I'm still building the Merkle tree from the entire corpus of data. I'm still rescanning the SS tables I scanned last time. So repair takes time proportional to the size of my data set. And when I start to get to terabyte-sized data sets, then that starts to become painful. We're talking hours, if not days, to build that tree for repair. Even if they're 100% in sync, I still have to scan the entire data set to repair. So what we're doing for 2.1 is we're going to say we're adding some intelligence to Cassandra about the repair process, so Cassandra can recognize, hey, those 6 SS tables on the left, I repaired those successfully last time, so this time I'm only going to build my Merkle tree based on what is new since the last successful repair. And so if I'm running repair regularly in my cluster, the repair time stays roughly constant instead of growing with my data set. We're also working on some improvements for cold data. So I showed in my diagram of the read process, how we have compression offsets and partition index and Bloom filter, and we allocate the same amount of memory to those structures, whether this SS table holds data that is read for every request or data that is read every million requests. So what we've done for 2.1 is we've allowed Cassandra to adjust how much memory it allocates to those and allocate more memory to the hot data to make it more efficient and use less memory for the cold data. Some things on the table for future work. Compaction is a fertile source of research papers because there is no such thing as an optimal way to do it. So there's different ways that different trade-offs we can make depending on our workload. So I mentioned that our first strategy comes from Bigtable, where we just combine SS tables that are of similar size, which isn't super intelligent and doesn't do a great job of throwing out obsolete data, but it does keep the number of SS tables manageable, and it's relatively fast because I'm doing relatively few merges of these SS tables. So this is good for workloads where I infrequently update rows. If I'm mostly inserting new rows, then size-cheat compaction does a fine job. We also added what we call leveled compaction. And the idea for this came from another Google project called LevelDB. What this does is it organizes the SS tables in what are called levels such that within each level, we're guaranteed to only have, there's only one SS table where that row could possibly exist. So in the worst case, in size-tiered compaction, if I have a row that is very hot and updated very frequently, it's possible that it could exist in every SS table on the machine. So I've colored SS tables that I need to read from in orange. So in leveled compaction, in my worst case scenario, I have to read from one SS table per level, and then in level 0 is unordered SS tables, so it's possible that it exists in every level 0 SS table. These levels are not to scale. Level 2 is actually 10 times as large as level 1. Level 3 is 10 times as large as level 2, and so forth. So that I could fit more than 2 levels on the slide. This is not to scale, but that's how that actually works. Now here's a pathological case for leveled compaction. Because it does a lot more work to make sure that there's only one, all the SS tables within a row are not overlapping, within a level are not overlapping. It's slower than size-tiered compaction, and it's possible for us to write out new SS tables faster than leveled compaction can keep up. And so you could get to a situation like this where I still have to read from most of the SS tables on the system because most of them are still in level 0 and they haven't been merged into the levels. So one thing we started doing with Cassandra 2.0 is we're doing size-tiered compaction within level 0 when it gets behind. So that keeps us from entering a vicious cycle of level 0 gets behind, so reads get slower, so there's less I/O to do compaction, so reads get slower still. So this keeps us from hitting that spiral of badness. The next thing that we're looking at doing that, as far as I know, nobody else has done, is keeping a probabilistic sample of the data in each SS table. In particular, what we care about is called cardinality estimation. And we're using hyperlog in particular. So instead of just doing blind compaction of saying, I'm going to combine SS tables that are approximately the same size, what hyperlog will let us do is say, I'm going to combine SS tables that actually contain overlapping data so that the compaction will actually be useful. This is a little bit hand-wavy because we actually haven't written the code for this yet, but I think it will work. We're also evaluating ways to do more data-aware compaction and being able to leverage our knowledge of the workload. If I'm doing append only or insert only workloads, I could actually get away without doing compaction at all. So it would be nice if there was some way that Cassandra could infer that from the writes that it gets, or maybe allow the user to give it some kind of hint to allow it to do that. So far, I don't know of a good way to do this. There's a lot of people that are really interested in finding out how to do this because it would help their workloads immensely. So we're motivated to figure this out, but I don't know of a good way to do this yet. Speaking of things that I don't have an answer to, when you do a delete from Cassandra, we actually write a special value. Remember, we have a log-structured storage engine. We can't just overwrite the existing row with null bytes or something. We actually have to append a new row that says this row doesn't exist anymore, and then compaction can throw away the old one by combining it with the tombstone. But because we have a distributed system, we actually have to keep tombstones around for a while. Because if a replica is down while I delete the row, then if I send out the tombstone, everyone deletes the tombstone, so there's no record at all of the row ever existing. Then when the replica that was down comes back online, he'll say, oh, hey guys, you're missing a row. And it will repair those with the row that was deleted. So what we do is we kind of have a cheat that says there's a configurable value called GC grace seconds, which is a bad word because it stands for garbage collection, and there's other things that do garbage collection in a Java server. So poor choice of configuration variable there, I'm sorry. But that says you are allowed to throw away tombstones after this many seconds, because we're just going to assume that any node that no node will be down for longer than this time period. It defaults to 10 days. So the rule is, if a node is longer than this time period, you are not allowed to just add it back to the cluster. You have to kill it and restart it as a new node and let it rebootstrap into the cluster, because at least if you're doing deletes, because any tombstones that it has missed while it was down may have been compacted away by now. So what this means is that, in particular, if I'm going with the default 10 days of tombstones, that could be a lot of tombstones if I have a workload that's doing a lot of inserts and a lot of deletes. And in fact, it's fairly easy to write a query that takes time proportional to the number of tombstones that it scans, because any tombstone that I see while I'm reading data for your query, I actually have to return that tombstone with the query to the coordinator so that I can do read repair with it, which means I'm going to compare that to the values returned by the other replicas, and I can make sure they have the proper tombstones. So as kind of a clumsy hammer to help people realize when they have entered tombstone hell and their performance is suffering because of it, is we have two other configuration variables: tombstone warn threshold, which will just log a warning when you scan more than this many tombstones, and tombstone failure threshold, which will abort your query and log an error, and your query will time out if you hit that many tombstones. So there's a couple orders of magnitude between these two, so hopefully you will see the warnings before you hit the failure threshold and start erroring out. And that'll give you time to make changes to your application to be smarter about tombstone usage. We have a blog post from my colleague in the back here about things that are bad to do with Cassandra, and one of those is writing a persistent queue, because you're constantly adding new events to the queue and constantly deleting events from the queue, so you're generating the maximum possible number of tombstones. So at this point, do I have time for questions? No. So should I offer to take questions outside the room? Would that be best? All right. Thank you for your time.